In this class, I am going to take the voltage standing wave ratio. Here you can see the definition of the voltage standing wave ratio. It is a mathematical expression of an electromagnetic field on a transmission line, such as coaxial cable. Usually, SWR, standing voltage ratio, is defined as the ratio of maximum voltage to the minimum voltage along the line. So we can write down V max by V minimum. So maximum voltage, which is upon the minimum voltage, which is the standing voltage ratio. Since it is a voltage, then it is VSWR. So in this figure we can see that there is a voltage source and it is a source impedance, and it is transmitting the power from source to the load through a cable. So Z0 is the characteristic impedance of the cable, and ZL is the load impedance, and ZS is the source impedance. This is the source impedance, and this is the impedance of this transmission line, which is called the characteristic impedance. The characteristic impedance, and this is the load impedance. We know that as per the maximum power transfer theorem, the power transmitted from source to the load is maximum when this impedance is exactly matches with the load impedance. And let us see that what is the characteristic impedance. The characteristic impedance is Z0, otherwise it is called as the surge impedance of a uniform transmission line, is the ratio of amplitude of voltage and the current of a signal wave propagating along the line. Here you can see that a section of transmission line, this is the current is flowing this direction, and below you can see that current is flowing in the opposite direction. This would be the current flow if it is phase and neutral. And we can see that there is a voltage vector, which is the difference of voltage between these 2 points. And here it is illustrated that a transmission line drawn as 2 black wires, and at a x distance into the line there is a current phasor Ix traveling through each wire, and there is a voltage difference phasor Vx between the wire. Then Z0 we can express as Vx upon Ix. So this is the characteristic impedance of the transmission line. So x represents the position of the distance of this transmission network from this point. So at this point, this is x. At this point, this is the voltage and this is the current. Then characteristic impedance of this line is V of x by I of x. I said earlier, the maximum power transfer occurs when the source impedance is equal to the load impedance. In some cases, this may not match. So what will happen? The amount of energy that is flowing from source to load, a part of which or full of it will be reflected back to the source. Now let's see that this is an electromagnetic signal which is transmitting through the telecommunication network. This is incident wave. This is an incident wave. This is traveling along this transmission network, and let's see that the source impedance is not exactly matching with the load impedance. What will happen? The energy will flow back. So there is a reflection wave. So this is a reflected wave. So there is an incident wave and reflected wave. So incident wave is source to load and reflected wave is from load to source because of the mismatch between the impedance of source and load. So these 2 waves will superimpose and will produce a standing wave. This is a wave which is traveling along the transmission line, and reflected wave is also traveling along the transmission line from load to source. But the standing wave, and with respect to any point of observation, it never travel in any distance, any direction. It never travel from load to source. It never travel from source to load. We cannot observe it as it is a traveling. It just, we can see that it is just oscillating. So if it is 0, then it is as a 0 point, and all the time. But it is a resultant of two waves, incident wave and reflected waves. And let's see more about this one in the next slide. If you look at this figure, you can clearly see that the V1 is the incident wave. This is the red color, the sinusoidal wave. And V2 is the reflected wave. Reflected wave is from the load to source, that is a reflected back. And the V is the resultant. And let us see the animation. Here you can see that this is one is traveling this direction, the another wave is traveling from right to left. So right to left wave is the reflected wave, and left to right is the transmitted wave or incident wave. And this is the resultant, the wave shape. If you look at, you can see that this wave, the black color wave, it is not traveling. It is just oscillating. You can see that this point is fixed. It is not traveling. This point is fixed. We can see that it is just oscillating, but it is traveling. But we cannot see that it is traveling because it is just the resultant of two voltage waves. One is traveling from source to load, another is traveling from load to source. So this is a standing wave. If it is a voltage, then it is voltage standing wave. The expression of voltage standing wave ratio is V max by V minimum. Now let us see that what is V max. V max is the sum of the incident wave and reflected wave. V minimum is the difference of incident wave and reflected wave. So if reflected wave and incident waves are of same magnitude, we can see that V minimum is this one. Okay. If reflected the wave and incident wave are of same magnitude, then V max would be here, because the wave shape will grow up to here, and this become 2 times the incident voltage or reflected voltage magnitude. And now let us put these values, this formula V max by V minimum. Let us substitute this expression here, V1 plus V2, which is upon V1 minus V2. Let us take V1 outside. So V1 get cancelled. So this become, let us use V2 by V1 is the reflection coefficient. Reflection coefficient. So reflection coefficient is the ratio of the reflected wave upon the incident wave. So the VSWR become 1 plus reflection coefficient, which is upon 1 minus the reflection coefficient. So this is the expression of voltage standing wave ratio. Now let us see that what would be the value of VSWR at different values of this reflection coefficient. So the maximum value of reflection coefficient is 1 and the minimum value of reflection coefficient is 0. if reflection coefficient is 1, then VSWR become 1 plus 1 by 1 minus 1, so it become infinity. If it is 0, VSWR become 1 plus 0 upon 1 minus 0. So the maximum and minimum value of VSWR is infinity and 1. Now let us see the shape of the reflected the voltage or current waveform when the source impedance and load impedance are of different values. And here you can see that a load impedance and the characteristic impedance of the line is exactly matching. In this case there is no standing waves. So here we can see that it is perfect, voltage waveform is perfect, there is no reflected wave. So this is happen at when the reflection coefficient, so here the reflection coefficient is 0. But now let's see that if the end of the transmission line is short circuited, where ZL equal to 0, that means that the load impedance is 0, it is completely short circuited. In that cases the reflection coefficient is minus 1. The wave shape of the resultant wave, which is the sum of incident wave and reflected wave, would look like this one. And in the third case, if the end of the transmission line is open circuited, that means the load impedance is infinity. So in that cases the reflection coefficient is 1, but if you see that the shape of the resultant wave, which is completely different from the above two cases. So these are the wave shape of the standing waves. Here there is no standing wave because there is no reflection, but here there is a reflection is there, and this is the standing wave. And in this case, last cases, when the transmission line end is open circuited, this is the standing wave.